Welcome back to the Deep Dive. Today we're jumping into, well, a really mind-bending area of physics, Albert Einstein's legacy. We're looking at the work charted by Kip Thorne, exploring Einstein's outrageous legacy.
That's right. Ideas like black holes, warping space-time, maybe even time travel. And what's amazing is how many of these concepts came purely from thought, from math, long before we could ever hope to, observe them. It really shows the power of his theory.
Absolutely. So our mission today is to unpack some of the wildest ideas, how relativity sort of forced black holes into existence. These, well, holes in space that literally curve space and warp time. And we'll touch on wormholes and time travel, too.
It all starts, really, with special relativity. That was the first big break from the old Newtonian way of thinking.
Right, Newtonian physics worked great for centuries, but it hit a wall with the speed of light. The Michelson-Morley experiment showed light speed was constant, always the same, no matter how you were moving.
Exactly. And that constancy, that universal speed limit, it just didn't fit Newton's framework. Einstein realized something fundamental about space and time themselves had to give.
But when it gave, it really shattered our everyday intuition, didn't it?
It did. Einstein took that one fact, light speed is absolute, and teased out the consequences. And they are profoundly weird. Two big ones usually come up first. One is length contraction. If you're speeding past me, I actually see your spaceship or whatever as being squished slightly in the direction you're moving.
And it's not a physical squishing, right? It's space itself contracting relative to me.
Precisely. The second is time dilation. From my perspective, watching you fly by, your clock seems to tick slower than mine. Your time is literally running slow compared to mine.
And these aren't just abstract ideas. I mean, we use this stuff, GPS, for instance.
Oh, absolutely. GPS satellites orbit fast enough, and they're in a weaker gravitational field, that both special and general relativity effects are significant. If engineers didn't constantly correct the satellite clocks for time dilation, your GPS navigation would drift off by several kilometers every single day. It's real, measurable physics.
Okay, so space and time aren't fixed. They stretch and shrink depending on motion.
Yes, and perhaps the most mind-bending consequence is the simultaneity breakdown. Because that speed limit is absolute for everyone, two events that happen at the exact same time for you might not happen at the same time for me if I'm moving relative to you.
So the order of events can change depending on who's looking.
The sequence of some events, yes. It means that space by itself and time by itself, they're not absolute, they're relative. Only when you weave them together into this four-dimensional fabric, space-time, do you get something that everyone can agree on, something independent of motion.
Okay, that sets the stage, but where does gravity fit into this new space-time picture? That required another leap, right? General relativity.
That was the next giant step, and it came from what Einstein called his happiest thought, the principle of equivalence. Basically, the idea is that gravity feels exactly the same as acceleration. Imagine you're in an elevator in deep space, no gravity. If the elevator accelerates upwards, you feel pushed down onto the floor, just like gravity.
Okay.
Now flip it. If you're in a sealed room on Earth and you drop your keys, they fall. But if that whole room were freely falling, say plummeting down a shaft, you and your keys would just float together. Inside that falling room, for that brief moment, gravity seems to vanish. Locally, physics behaves just as it would in empty space, following the rules of special relativity.
So free fall cancels gravity locally, but gravity obviously still exists on a larger scale. The Earth is still pulling.
Right. While free fall gets rid of the overall pull, you can still detect gravity's presence through what we call tidal gravity. Think about falling feet first towards a planet. Your feet are slightly closer than your head, so the gravitational pull is a tiny bit stronger on your feet. You get stretched.
The spaghettification idea near a black hole comes from that.
Exactly that kind of differential force. If you were falling sideways, you'd feel squeezed instead of stretched. These tidal forces, the stretching and squeezing, they're the real signature of gravity's curvature.
So gravity isn't a force pulling things across space-time. It is the curvature of space-time, caused by mass and energy.
That's the core idea of general relativity. Objects like planets or light rays aren't being pulled, they're just following the straightest possible paths, we call them geodesics, through this curved four-dimensional landscape.
And once you see gravity as geometry, black holes almost seem inevitable.
They become, well, compulsory under the right conditions. If you curve space-time enough, by packing enough mass into a small space, you can create a region where the curvature is so extreme that even light can't follow a path out.
It's interesting that the basic concept, a dark star, actually predates Einstein quite a bit. Michel and Laplace in the 18th century.
Yeah, using Newtonian gravity and the old idea of light as particles. They figured if a star was dense enough, its escape velocity could exceed the speed of light. For the sun's mass, they calculated the critical size would be an 18.5-kilometer circumference. Remarkably close, actually.
But Einstein himself, even though his own GR equations pointed towards this kind of collapse,
Yeah.
he didn't like it.
No, he initially resisted it strongly. He thought nature would find a way to prevent such a total collapse. He famously said the idea smelled wrong to him.
Which highlights a big struggle in physics for decades, trying to find ways around black holes, finding stable endpoints for massive structures, stellar graveyards.
Exactly. The first kind of graveyard discovered was the white dwarf. These are the leftover cores of sun-like stars. They're incredibly dense, held up against gravity not by heat or fusion, but by something called electron degeneracy pressure, quantum mechanics, basically.
But there's a limit to how much mass that pressure can support, the Chandrasekhar limit.
That's right. Subramanian Chandrasekhar calculated this in the 1930s. He found that if a non-rotating white dwarf gets heavier than about 1.4 times the mass of our sun, electron pressure fails. It can't hold up anymore.
And that led to a huge fight with Arthur Eddington, the leading astrophysicist at the time.
Oh, a famous clash. Eddington just couldn't accept that a star could keep collapsing indefinitely. He publicly ridiculed Chandrasekhar's calculation, suggesting relativity was being misapplied. He really resisted the implication of unstoppable collapse.
But Chandrasekhar was right. If the star core is heavier than 1.4 solar masses,
It collapses further. The next possible stopping point is a neutron star. Here, gravity is so intense it crushes protons and electrons together to form neutrons. The entire star becomes like a giant atomic nucleus, held up by neutron degeneracy pressure.
it's another quantum mechanical effect. But even that has a limit, right?
It does. Neutron stars can only support up to about 2 solar masses, maybe a little more. The exact limit is still debated. We call it the Tolman-Oppenheimer-Volkoff limit.
So, the implication is unavoidable then. If a dying star leaves behind a core heavier than, say, 2 suns, and it can't somehow shed that extra mass,
Then there's nothing known in physics that can stop gravity. Electron pressure fails, neutron pressure fails, the collapse must continue.
all the way down.
All the way down. It must shrink past the point of no return, forming a singularity and an event horizon. A black hole. Oppenheimer and Snyder modeled this mathematically back in 1939 for a simplified spherical star. They showed that from a distant observer's viewpoint, the star's surface seems to slow down as it approaches that critical boundary, the event horizon. Its light gets redder and dimmer, it appears to freeze there.
Which explains the old term frozen star.
Exactly. But for someone falling with the star's surface, the collapse continues right through the horizon in a finite amount of time. Relativity in action.
Okay, so they must form. What are they actually like, these holes in spacetime? You mentioned earlier they're surprisingly simple, the no-hair idea.
Yes, the no-hair theorem. It's a wonderfully descriptive phrase. It means that once a black hole settles down, it's defined by just 3 properties. That's it.
Only 3, after all the complexity of a star collapsing.
Just 3. Its total mass, its angular momentum, how fast it's spinning, and its overall electrical charge, which is usually assumed to be zero or very close to it for astrophysical black holes.
So all the other details.
Yep.
The star's chemical composition, its magnetic fields, whether it had mountains, all gone.
All gone, or rather radiated away during the collapse. If the star had a magnetic field, that hair gets shed as electromagnetic waves. If it had bumps or irregularities, those get smoothed out by radiating gravitational waves. This was rigorously shown by Werner Israel, Brandon Carter, Stephen Hawking, and notably Price's theorem showed how the hair gets radiated away. The end state is incredibly clean.
That's profound. Gravity erases almost all information, leaving just mass, spin, and charge.
It really simplifies things at the ultimate level.
But you said spin is one of the key properties. And spin seems to make black holes far from simple bystanders. Quasars, for instance.
Spin has dramatic effects. A spinning black hole doesn't just curve space-time, it drags space-time around with it. It's called frame dragging. It creates this vortex, this swirling region of space-time outside the event horizon called the ergosphere. Anything falling in gets forced to rotate with the hole.
And we see evidence of massive spinning black holes out there.
Oh, yes. Especially in the centers of galaxies and quasars, we found supermassive black holes weighing millions, even billions of times the mass of our sun, like the one in the quasar core Thorne mentions, 2 billion solar masses. And these giants are often spinning incredibly fast, near the theoretical maximum speed. Probably because they grew by slurping up matter from rotating accretion disks over cosmic time.
And that spin is the power source for those enormous jets we see shooting out of quasars and active galaxies.
It's thought to be a key part of it. The leading model is the Blandford-Znajek process. Basically, the spinning black hole acts like a giant conductor rotating in a magnetic field, provided by the accretion disk. This sets up huge electrical potentials. It effectively extracts rotational energy from the black hole itself, flinging particles out along the spin axis in those powerful jets. The black hole powers the jet by slowing its own spin.
Incredible. Okay, so theory predicted them. We know their basic properties.
Yeah.
How do we actually find these things? They're black, after all.
Right, you can't see them directly. The key was looking for their gravitational effect on something else we can see. Yakov Zeldovich had the crucial idea in the 1960s. Look for binary star systems where you see a normal star orbiting nothing, an invisible companion.
You track the visible star's motion.
Exactly. You use the Doppler shift in its light to measure its orbital speed and period. From that, using Kepler's laws, you can calculate the mass of the unseen companion.
And if that calculated mass is too big to be a white dwarf or a neutron star,
Then your prime suspect is a black hole. Say, if the invisible object weighs 5 or 10 solar masses, it's really hard to explain it as anything else.
which led to the first really strong candidate, Cygnus X1.
Yes, Cygnus X1, discovered around 1971-72, it's a bright X-ray source. The X-rays come from gas being stripped off a visible supergent star and falling towards the invisible companion. This gas forms an accretion disk, gets incredibly hot, millions of degrees, and radiates X-rays just before it disappears into the black hole.
And the orbital motion of the visible star showed the companion was hefty.
Definitely. Estimates put its mass well above the neutron star limit, maybe 15 solar masses or more. It became the poster child for stellar mass black holes.
Okay, that firmly grounds black holes in observation. Now let's shift gears to the really speculative stuff. Wormholes. This came out of Carl Sagan trying to write his novel Contact scientifically accurately.
It did. Sagan wanted a plausible way for his characters to travel vast interstellar distances quickly. He initially thought about just using a black hole, but Thorne, whom he consulted, pointed out that wouldn't work. You'd hit the singularity. So Thorne explored if Einstein's equations allowed for a shortcut, a tunnel through space-time connecting, say, Earth to Vega 26 light-years away via maybe a kilometer-long tunnel.
A traversable wormhole. Sounds like pure science fiction. What's the catch, physically?
The catch is keeping the tunnel open. According to general relativity, the throat of such a wormhole would naturally want to pinch off almost instantly due to its own gravity. To hold it open, you need something with anti-gravitational properties. You need exotic material.
Exotic material.
Meaning material that has a negative average energy density. Normal matter and energy curve space-time one way, attractively. This stuff would have to curve it the other way, repulsively. It exerts negative pressure, pushing outward.
Does anything like that actually exist?
Not that we've ever seen or manipulated in bulk, but quantum field theory does allow for fleeting fluctuations of negative energy density in the vacuum, for instance, near a black hole's event horizon. So it's not completely ruled out by known physics, but whether you could gather enough of it and stabilize it to hold a macroscopic wormhole open, that's a huge unknown. Very speculative.
But if, hypothetically, some super advanced civilization could build and stabilize a wormhole, then comes the really wild part, time travel.
That's the next logical step arising from special relativity again. Imagine you have a wormhole connecting 2 points in space. Let's say you leave one mouth here near Earth and you take the other mouth on a spaceship journey. You accelerate the moving mouth to near light speed, travel for a while, then bring it back and place it near the first mouth.
Okay, time dilation comes into play. The traveling mouth experiences less time.
Exactly. So if you look through the mouths, the stationary mouth might show the year 2050, but the mouth that traveled might show the year 2049. Time is out of sync. Now, if you step into the 2050 mouth, you could potentially emerge from the other mouth in 2049. You've traveled back 1 year in time. The wormhole has become a time machine.
Which instantly brings up all the paradoxes. The grandfather paradox, or Polchinski's billiard ball paradox you mentioned to Paul, goes back in time to knock its earlier self away from the time machine entrance.
Right. What happens? Does the universe just forbid it?
Yeah.
Well, Thorne and his students explored this, particularly using quantum mechanics. What they found was interesting. For situations like the billiard ball, classical physics seems to allow for self-consistent solutions, even with the time loop. The paradoxical initial condition, sending the ball straight at its younger self, might be impossible, but slight variations are possible. The ball could go back and, say, just glance off its younger self, altering its path just enough to avoid the direct collision but still allowing the time travel to occur.
So the laws adjust to prevent a true paradox, allowing multiple consistent histories.
That's one interpretation. Quantum mechanics suggests that all possible self-consistent paths could exist simultaneously, each with a certain probability. No paradox is actually created, just weirdness.
But there's also a counter idea, isn't there? Hawking's conjecture.
Yes, Stephen Hawking proposed the chronology protection conjecture. He suspected that the fundamental laws of physics might actually conspire to prevent time travel on macroscopic scales. The idea is that just as a wormhole is about to become capable of forming closed time loops, quantum effects might run wild. Virtual particles circulating through the wormhole could build up into an infinitely energetic feedback loop, destroying the wormhole itself.
Nature protecting the timeline.
Sort of, yeah. It's a compelling idea, but still a conjecture. We don't have the full theory of quantum gravity needed to prove it one way or the other.
So, looking back at this whole journey, we started with special relativity breaking classical physics, moved through general relativity mandating black holes, saw how we found them, and ended up in this realm of wormholes and potential time machines based on the same physics. It's quite an arc.
It really is. And the historical lesson is powerful. Think about how fiercely ideas like black holes or even continental drift back in geology were resisted, sometimes for decades. Yet the evidence eventually forced scientists to accept them. They went from outrageous speculation to just facts about the universe.
It gives you a sense that physics might actually be converging on something real, doesn't it?
Yeah.
A sequence of deeper laws.
Yeah.
Newton, then SR, then GR, then quantum mechanics.
Many physicists feel that way, that we're peeling back layers, getting closer to some ultimate set of rules. The big hurdle now, the frontier, is unifying general relativity, our theory of gravity on the large scale, with quantum field theory, our theory of particles and forces on the small scale. Quantum gravity.
The theory of everything, potentially.
That's the dream, a single framework describing all forces and particles.
So if that convergence is real, and maybe the next century brings us that unified theory of quantum gravity, here's the final thought for you, our listener, to ponder. What currently unimaginable, truly outrageous predictions might that final set of laws reveal? What new compulsory features of reality are waiting just beyond our current understanding? Thank you for diving deep with us today.